Let's start with ACT Science Passage 1. So, two measures of water quality are the number of E. coli bacteria present and the biotic index, which is a numerical value based on all of these different factors. Both of the measures can be affected by water flow. Great. So let's look at the charts that we're given about all these things. So E. coli levels that are above 100 colonies formed per 100 milliliters of water indicate reduced water quality. So high E. coli means low water quality. That's good to remember. Okay. And we have a graph for site 1 and for site 2 of E. coli per 100 milliliters on certain days. And that's our figure 1. Let's look at our next table. Table 1 shows how water quality rating varies with biotic index. So we see here, right, this goes from 1.0 all the way up to 3.6, and it's increasing. And this is water quality going from poor, fair, good, excellent. So it's also increasing. Great. And let's look at table 2. So this has site 1's average biotic index and site 2's average biotic index. So it looks like site 1 is at about 6.3. That's excellent. That's great. We can write that down in case we need it later. It's good to be able to make sure that we understand the terms real fast, but don't take too much time on these steps. And 2.5 is right and fair. Great. These could be useful later. Figure 2 shows the water flow at each site in the 5 collection days. So we know water quality and water flow are somehow related. We haven't really explored that yet, but let's just look at this graph. So it looks like it's water flow and figure 2, and it's for certain days for site 1 and site 2. Great. Question 1 asks if an E. coli level of over 400 colonies formed per 100 milliliters of water is unsafe for swimming, on which of the following collection days at what site would it have been unsafe to swim? So our graph already shows E. coli colonies per 100 milliliters. Perfect. So we just need to look for anything that's around 400. And it's pretty clear that there's only one that's really approaching 400, and that is day 30 for site 1. So let's go with that. Question 2 says, based on figures 1 and 2, so we only considered the two graphs, consider the average water flow of the average E. coli level for site 1 and site 2 over the period. Which of the sites had higher average water flow and which had higher average E. coli level? So we're only really comparing two. And we could do the math, but I don't think we need to here, right? So if we look at figure 1, we see that site 1 is higher for almost every single one, right? This one is significantly higher. This one it's lower, but only by 1. So it doesn't really matter to us, and these two are equal. So it's pretty obvious that here site 1 is much higher. So we know that site 1 is higher for E. coli level. So we don't want G or J. It's going to be F or H. Let's look at figure 2. Once again here, there are not even any number labels. We don't need them, right? We see that it's higher at site 1 for all 5. So by quickly scanning the graph, we can tell that it's going to be site 1 for this one too. That gives us answer F. Question 3 says, according to table 1, what is the relationship between water quality and biotic index? So looking at table 1, it looks like as biotic index increases, water quality increases, right? We looked at that when we were previewing the text. So let's look at the answer that it says that. So it looks like A is the one that we want. Question 4 asks, as water quality improves, the number of stonefly larvae increase. Students hypothesized that more stonefly larvae would be found at site 1 than at site 2. Are the data presented in table 2 consistent with this hypothesis? So this is table 2. This is the only thing we want to consider. So don't worry about E. coli, don't worry about water flow, just this, right? So it looks like, yeah, site 1 has higher water quality, and it says right here that higher quality means higher larvae. So yeah, we agree with these students, but let's look at the options for yes. We know it's not going to be H or J because we're looking at yes. So it says yes, based on biotic index. Site 1 has a water quality rating of good, and site 2 has a water quality rating of poor. But if we look at what we discovered earlier with excellent and fair, this isn't quite true, right? It's not good and poor, it's excellent and fair, so it's not going to be F. And then G says yes, based on biotic index. Site 1 has a water quality rating of excellent, which yeah, we agree with. And site 2 has water quality rating of fair. Perfect. Answer is G. Question 5 asks, which set of data best supports the claim that site 1 has lower water quality than site 2? So looking at our graphs, it looks like water flow we're not so sure about the quality of. Both the biotic index tables show that site 1 is higher. But then if we look at site 2, right, it says right here, if we have more E. coli, we'll have decreased water quality. And we definitely have more E. coli here at site 1. So let's go with figure 1. So just want to check the labels right below. We know it's figure 1. Question 6 asks, suppose large amounts of fertilizer from adjacent fields begin to enter the river at site 1. The biotic index of the site will most likely change in which of the following ways? So if there's more fertilizer, that means the water quality is going to go down because that's not pure water. If water quality decreases, right, if we look up at this table, if this decreases, then biotic index should decrease as well. So we want to pick the one that says decrease because water quality is likely to decrease. So this requires a little bit of outside knowledge. But in general, a big summary with this set of plots is that we should always consider exactly the data that we're given by the passage, not any outside knowledge we're trying to corroborate from points that they don't mention. If they say look at figures 1 and 2, only look at figures 1 and 2. Move on to passage 2, which is about aluminum water-based paints, so AWPs. Contain flakes that give things a shiny appearance, and if the flakes corrode, a dull coating of aluminum hydroxide forms on them. And we have this nice equation. So aluminum and water equals aluminum hydroxide, that's AlOH3, and hydrogen. Great. So table 1 shows the volume of hydrogen gas produced over time at 25 degrees Celsius in 1 atmosphere for 100 milliliter samples of freshly made AWPs 1, 2, 3. So we have 3 different samples in 3 separate trials. They were all identical except they had a different concentration of DMEA, an AWP ingredient that increases pH. So we have 3 different samples at different pH levels, and we're going to look at the hydrogen production. So let's just think for a second, why do we care about hydrogen production? Well, you don't want to dote over the passages for too long. It's important to try and get the connection between each of the tables. So it looks like up here, hydrogen is produced when the aluminum corrodes. So basically, aluminum corrosion is related to hydrogen production. So the more hydrogen produced, the more the aluminum corroded, which is probably bad. Anyway, the AWP trial was repeated 4 times, but for each trial, the sample had a different concentration of 1 of 4 corrosion inhibitors. So inhibitors are things that slow stuff down. So that's important, right? So we have these different acids and items, and for different amounts, they slowed down corrosion at different levels. Again, we have volume of hydrogen is the thing we're measuring. So we're saying more hydrogen produced means more corrosion. Great. So based on table 1, which of the following graphs shows how the volume of hydrogen produced by AWP2 changed over time? So if we're looking at AWP2, we're looking at this row. And we want to see which of these graphs this value well. So we have volume of hydrogen and day, which is the exact same unit we have here, which is really nice. So for day 2, we should have 21. So it looks like this one, yeah, that's like 21. Very close to 0 because we're on the hundredth scale. These ones are no longer it, right? On day 2, they're at like 800. Next, we want about 187 for the next day. So for day 4. So that's like 187, yeah, just under 200. Perfect. And the next one is 461 on day 6. So if we look at option A, we're pretty high on day 6. That's like 600, but let's check anyways. This one is a lot more reasonable right here. That's like 461. Day 8 now has 760. So yeah, this is 760, and this is as well. The difference is going to be this value here. So we don't like the 6 here, so we're going to go with B. That one most clearly graphs each value. Right? It could probably be better, but that's fine. Question 8 asks, based on table 1, the volume of hydrogen produced by day 10 from the AWP1 sample has been measured. It would most likely have been blank. So if we look at the changes, right, we go from 4 to 33, right, to 81 to 133. So we're increasing by about 50 every time. From day 2 to day 4, it's a little smaller, but basically we're consistently increasing, and it's like plus 50. So 50 plus 133 is kind of what the ballpark we're looking for. So we're not less than 133. Between 133 and 461 seems about right. That's a really big margin. But let's just check the other two first. So between 461 and 760, absolutely not, right? We're looking at like 50 plus 133, so like 183 maybe, not 460. And greater than 760 is equally out of the question. Okay. Question 9 asks, according to table 1, what volume of hydrogen was produced by AWP1 from the time volume was measured on day 6 to the time it was measured on day 8? So if we look, we have 81 on day 6 and 133 on day 8. So if we do some quick subtraction, right? So 3 minus 1 is 2, 13 minus 8 is 5, we have 52 milliliters. Great, that's option A. Question 10 says, in the trials represented by table 1 and figure 1, so this is figure 1, and then table 1 is up there, by measuring the volume of hydrogen, the experimenters were able to monitor the rate at which, so we talked about this earlier, right? We're looking at this equation up here. So aluminum and water equal aluminum hydroxide and hydrogen. So water is converted to aluminum, not quite, right? They combine. Aluminum is converted to water. Once again, it's just the inverse, it's still not correct. Aluminum is converted to aluminum hydroxide, so we like that one. But let's check the last one. Aluminum hydroxide is converted to aluminum. So we're actually looking for the inverse of that, right? We're looking for when aluminum corrodes, H. Question 11 says, based on the passage, DMEA is most likely an acid or a base. So let's scroll up to where we describe DMEA, and we find that it increases pH. Great that we took note of that. So pH is a measure of how acidic a substance is, and a lower pH means it's more acidic. That's one of the prior knowledge facts that it's really nice to remember, that an acid is going to have a pH of like 1, 2, 3. A base is going to have a pH of like 8, 9, 10. So here it increases pH. If it increases pH, that means it's probably going to be basic, because the bases have high pH values. Question 12 says, consider the volume of hydrogen produced by day 2 from the AWP3 sample that contained no corrosion inhibitor. Based on table 1 and figure 1, the AWP3 sample considering EDTA produced approximately the same value of hydrogen by which of the following days? So it looks like on day 2, the third sample produced about 121 hydrogen molecules. And if we look here, we're looking for the one that's like EDTA, so it's like dot dash dot dash dot dash dot dash reaches 121, like right here, around day 10. So day 10. It's our choice, right? These are all significantly lower. By day 7, it's like still below 100 and lower from there before. So in summary for this passage, while it's important to take a look at the figures, as I mentioned before, it's important not to obsess over them. Once you get the main point, especially the connections between the figures, you should move on to the questions. Because if you look, this last graph was pretty complicated, but we barely looked at it. So we didn't want to waste too much time reading all of the details.